Hello everyone. A very good evening to one and all of you. I hope I'm audible and visible. So let's wait for 5 to 10 minutes so that everyone can able to join this session. Okay, let's start the session. Hello everyone, my name is Pooja Verma. I am PMRF Research Scholar from IIT Kharagpur and instructor for this course, Professor Syamal Kumar Das Mandal, Advanced Technology Development Center, IIT Kharagpur. This is a week 8 live and interactive session on signal processing techniques and its applications. So I hope all of you have gone through this week video lectures. So these are the some contents which have been covered for this week, that is digital filters, FIR filters, that is finite impulse response filters, linear symmetric and anti-symmetric filters, FIR filter design and frequency sampling method. Okay, so first we will go through some theoretical concepts, then we will solve some problems. Okay, so let's see what is a digital filter and how we can design the digital filter. So this is a frequency response of an digital filter where omega s is normalized as a of a stop band frequency and omega p is a pass band frequency. Del s is peak ripple in stop band and del p is at the peak ripple in the pass band. So till here it is a pass band frequency. After here to here it is a stop band frequency, and that is omega s minus omega p. It is represented as a transition bandwidth that is represented by del of omega. Okay, just a minute. Okay, so my pen is not working, so we will move forward, then I will check it. Okay, so here that is a description of that where is the pass band frequency belongs 0 to omega belongs to 0 to omega p, that is a pass band frequency. Okay, and in that case mod of that function is equal to 1, and that pass band ripple will vary from plus minus del of p, and that is 1 minus del p, where then the whole function will vary from the amplitude of that function or that frequency will vary 1 minus del p to 1 plus del p. Okay, and the pass band stop band frequency will vary omega s to pi, and in that case the amplitude of that function will be h e to the power j omega is equal to 0, and del is a peak ripple in the stop band. Already we know that. So how we will find out the peak ripple? That is represented in the alpha p, that is represented by in the pass band, that is equal to minus 20 log 10 1 minus del p in dV, and similarly in the stop band the peak ripples factor will be represented by a del a, alpha s, that is minus 20 log 10 del s. Okay, now what is a FIR filter? So FIR filters is a finite impulse response. That means that is a finite, that will be a finite impulse function. So it is a discrete linear time invariant system whose output is based on the weighted summation of finite number of past inputs. So the finite impulse response will, the equation is h of z in the z transform is equal to n varies 0 to n, that is n minus 1. So that will be the n minus 1 h of n z of minus n. So the impulse response is required to be a linear phase. The filter coefficient must be satisfies this constant, that is h of n is equal to plus minus h of in brackets n minus and it is also called symmetricity and anti-symmetricity property. Okay. Okay, so for a symmetric unit sample response of h of n, the number of filters coefficients that satisfy the frequency response is, that is, m plus 1 divided by 2, where when m is odd, and m divided by 2 when m is even. And for antisymmetric unit sample response function, the number of filter coefficient must satisfy this, that is, m minus 1 divided by 2 when m is odd, and m divided by 2 when m is even. Okay. Now next, how we will solve the FIR filter design problems. So there are three methods to solve the FIR filter design. That is, first one is window series approach, Fourier series approach. Second is frequency sampling approach, and third one is a computer-based optimization method, that is solved by any function, MATLAB or any other. And this is a frequency sampling and Fourier series approach we will see. So in the window series Fourier series approach, you have stated must be there this type of a window function, that is a rectangular window function, Bartlett, Hanning, Hamming, and Plackman, and their frequency responses and their transition width of the main lobe and peak side lobes are given in this table. So we will use this while solving the questions or problems. Okay. So these are the commonly used window function or window Fourier series windowing approach. Okay. Now next one is the frequency sampling method. So in the frequency sampling method, there are two types of frequency sampling method, and here it is also symmetric and anti-symmetric. So here I have taken these slides because of we will use this while solving our problems. Okay. So in the type 1, so here you will see when n is even, so this type of circular convolution will be represented, and when n is odd and type 1, there is this type of. So here only one function will be at this, and all other not in the that line, and here all the fours are on that, all the zeros are in that pole, all the poles are in that line, 0, 90, 180, and 360. Similarly for type 2 also, there if n is even, there is a difference between type 1 and type 2 based on the equation. So in the type 2, here there is a one pole on the in that line, and in the type 2, and when n is even, there is a no poles on that line. So these are the equations for type 1 and type 2. We will use that. Okay, now symmetric, where for alpha is equal to 0, for alpha is equal to 1 by 2. These are the equation where gk will equal to minus 1 to the power k hr 2 pi k divided by n. We will solve based on that. Okay, we will solve some problem based on that. Okay, so I am moving here for similarly for antisymmetric. So here we are moving to solve some problems. So question 1 is, which of the following is the difference equation of the FIR filter of length m, input xn and output yn? So which option is correct for this one? Can you answer in the chat box? So I will wait for a few seconds, then I will elaborate it. Please try to answer in the chat box till Okay. So question 1 is which of the following is the difference equation of the FIR filter of length m, input xn and output phi of n. So the correct for FIR filter he has seen the what is the difference equation for the FIR filter with length m. So we have seen this is a commonly FIR filter equation, that is n vary from 0 to m minus 1, that is length of the filter, that is bk x n minus k. It is in the frequency domain, sorry, it is in the time domain. So we have seen in the frequency domain, so you can convert it. So you will get, when you will convert it into frequency domain or Z transform, you will get, but here they have asked in the time domain only, so that's why I have written this equation. Okay, so this is a basic difference equation for an FIR filter. Okay, so the FIR filter equation, that is represented, output represented by y of n and input is represented by x of n with shifted version. Okay, but it is a finite impulse response and Vk is a set of filter coefficients. Vk is filter coefficients. Coefficients here. And x n minus k ensure that the filter operates in the causal manner. That means the output depends on time in the present or past input, does not depend on the future input. This is a finite impulse response because it does not depend on the future value. It depends only on present or past values. Okay, so this is a basic question for the, so option A, here it is given y of n is equal to k varies 0 to m plus 1 bk x plus x n plus k. Here we can see that n plus k, n is equal to, so it will depends on the, it is depending on the future value, so it will not a correct option. Similarly for option B, here it is m plus 1, so the summation goes up to m plus 1, so it cannot be a correct, it is a not a correct one. Now next option C, option C is y of n is equal to k is equal 0 to m minus 1 bk x n minus k. So it depends on the present and past value. So this one is the correct answer for this question. Option D is none of the mentioned. So option C is matching with this equation. So option C is the correct answer for this question. Okay. Okay. So moving to the next question. Now next question is, what is the approximate transition width of the main lobe of a Hamming window? So which option can be a correct answer? What is the transition width of a main lobe of a Hamming window? Okay, so already we have seen in the previous table also. So transition width of the main lobe in the case of Hamming window, for Hamming window, that is Hamming window, transition bandwidth, already we know that del of omega, it is represented by del of omega, so it is equal to 8 pi by m, where m is the length of the window. So correct option is B, 8 pi by m. For Hamming and Hamming window, the transition width of the main lobe is 8 pi by m. Okay. Okay, moving to the next question. Our next question is, consider a 51 tap linear phase FIR filter operating at a sampling frequency of 10 kHz. The delay of the linear phase FIR filter is. So option A is 2.55 milliseconds, option B is 5 millisecond, option C is 5.1 millisecond, and option D is 2.5 millisecond. So how we can solve this question or this problem? Okay, so actually my pen is not working correctly, so that's why I'm not able to write. So I'm trying. Okay, so the linear phase FIR filter with an odd number of, here m is given as a m is equal to 1. So that means it is a odd number of taps. It is odd number of filters that have been used. Sampling frequency is given as fs is equal to 10 kilohertz. 10 kilohertz. So they have asked the delay of the linear phase FIR filter. So for that, the formula is to calculate a delay. Delay is equal to m minus 1 divided by 2 into Ts. And already we know that, so Fs Ts or Ts is equal to 1 by Fs, right? Here the sampling frequency is given. So delay, how we can calculate it? Delay is equal to m is given, that is 51. So 51 minus 1 divided by 2. Ts is equal to 1 by Fs, right? So Fs, so if you put the value of Fs, so 50 divided by 2, and Fs is 10 kilohertz, 10 to the power 3, right? So 25. So after that I am solving here. So you will get 2.5, here 25 divided by 10 kilohertz. So 10 to the power minus 3, right? Minus 3. So how much it is? 2.5 milli. 10 to the power minus 3, we have called it millisecond. So 2.5 millisecond. Okay, so option D is the correct answer. 2.5 millisecond. Okay. Okay, so I hope you have understand this. So moving to the next question. Now next question is FIR filters. One is are non-recursive, two is don't adopt any feedback, three is are recursive, and four is use feedback. So options are given which are the FIR filters. What are the properties of the FIR filter? A is 1 and 2 are correct. Option B is 3 and 4 are correct. Option C is 1 and 4 are correct. And option D is 2 and 3 are correct. So here detailed answer is here I have written. Okay. So FIR finite impulse response filters have the following characteristics. So one is are non-recursive. So FIR filters don't use previous outputs value in their computation. So meaning they are inherently non-recursive, and they don't adopt any feedback. So it is a finite impulse response. So they are rely only current and past input values without feedback from the previous outputs. Okay, and are recursive. So FIR filter are not recursive. filters, already we have seen that. So recursive filters use feedback. Recursive filters are using the feedbacks. So which are the characteristics of the IIR filters, not a FIR filters? And so the recursive filters use feedback. So option 4 is also not a that use feedback. So don't use any feedback. FIR filter don't use any feedback. Okay, so final answer is that FIR filters are not non-recursive and don't use any feedback. So option 1 and 2 are the only correct answer for this question. Okay. Okay, so I hope you have understand. So moving to the next question. Now next question is H of n is an antisymmetric unit sample response of a linear phase FIR filter. If the order of the filter is 89, determine the number of filter coefficients that specify the frequency response. Okay, so please try for this question, at least try to answer this question, then we will solve it. Okay, so let's solve this question. Okay, as we know that for an antisymmetric filter, h of n is equal to h m minus 1 divided by 2 is equal to 0. And thus number of filters when m is odd is m minus 1 divided by 2 when m is odd and m divided by 2 when m is even, right? So here m is given as a 89 number of filters, so it is odd. So total filter coefficients will be, that is m minus 1 divided by 2, that is 89 minus 1 divided by 2. So it is 88 divided by 2 is equal to 44, right? 44. So option A is the correct answer for this question. Okay, so I hope you have understand. So moving to the next question. Now next question is, which one of the following is the advantage of FIR filter over FIR filter? So option A is FIR filter can have an exact linear phase. Option B is FIR filter is always unstable. Option C, for FIR filter, the design methods are non-linear. And option D, FIR filter cannot be realized efficiently in hardware. So detailed analysis I have written here, but in that case you can give the answer. So which option can be a correct answer? Yeah. Which one of the following is the advantage of FIR filter over IR filter? So option A is FIR filter can have an exact linear phase. So yes, FIR, that means finite impulse response, and that they are the exact linear phase. So FIR filter is always stable, sorry, is always unstable. So FIR stands for finite impulse response. So it is a finite duration signal, so it is a stable signal, not a unstable signal. Okay, and for FIR filter, the design methods are non-linear. So that is also incorrect. FIR filter design methods such as a windowing, frequency sampling, and Park MC-Klein algorithm are systematic and not a non-linear. Okay, so FIR filter cannot be realized efficiently in the hardware, so it is also incorrect. So FIR filter is finite impulse response. So FIR filters can be efficiently implemented in the hardware, especially in this DSP processors and FPGAs. So although they may require more computational resources compared to IR filter. So it is also incorrect. So only option A is the correct answer. FIR filters can be designed to have an exact linear phase. That means their phase response is a linear function of frequency. Okay. So option A is the correct answer for this question. Okay, now moving to the next question. If a filter has a 60 dB bandwidth of 10 kilohertz and 3 dB bandwidth of 4 kilohertz, the shape factor will be. What will be the shape factor and how we can determine this? Okay, so the shape factor of any filter can be defined by the shape factor of filter is equal to, that is if two frequency and bandwidths are given, so 60 dB, that bandwidth 1, 60 dB bandwidth divided by 30 dB bandwidth, or simply it is defined by a shape factor is equal to, in general I can write it, in general shape factor is equal to bandwidth 1 divided by bandwidth 2. Okay, so 60 dB bandwidth, here bandwidth 1 is, so it is given as a 10 kilohertz. Okay, so that is 10 kilohertz and 3 dB bandwidth is equal to 4 kilohertz, right? So it will left 10 by 4 and that is equal to 2.5. Okay, so it is equal to 2.5. So option D is the correct answer for this question. Okay, okay, so now I hope you have understood. So moving to the next question. Now next question is, H of n is a real valued linear phase finite length filter. If 3 plus 4j is a zero of the filter, then which of the following is are also a zeros of that filter, of the filters? So here one zero is given. So what are the other zeros of that filter? So in case of linear phase FIR filter, to have one zero, let's see there is a 10, so I can write it here. In case of linear phase FIR filter, to have 10, that is Z0. So here Z0 is 3 plus 4j. Okay, then other zeros will be or other zeros are, that is first one Z0, then its opposite, that is 1 plus 1 divided by Z0, and what are the other? If it is a conjugate, so complex number, so it is a Z of conjugate, and then other one is also 1 by Z0 conjugate. So these are the zeros of that FIR filter. So here Z0 is given 3 plus 4j. What are the other zeros are there then? Then it is a 1 by 3 plus 4j, right? Now parallelly you can calculate and tell me what will be 1 divided 3 plus 4j value. Can you tell me? And then other one is Z0 conjugate, that is 3 minus 4j will be there, and 1 by z. So it is 1 by 3 minus 4j. So can you calculate me and let me know? So when you will divide it, you will get 0.12 minus 0.16j, and similarly here 0.12 plus 0.16j. So these are the other four zeros of that filter. So 3 plus 4j, 3 minus 4j, 0.12 minus 0.16j, and 0.12 plus 0.16j. So just match with the answers. So option B is the correct answer for this question. Okay. Okay, I hope you have understand. So moving to the next question. Now next question is the phase of a linear phase FIR filter of length n is equal to 13 is. What is the phase of that linear phase FIR filter where n is equal to 13 is given? That means length of the filter is given. Length of filter n is equal to 13 is given. So the phase of linear phase FIR filter, that is represented by phase, we know that represented by theta of omega, that is equal to a minus a omega, where a, that is ripple or magnitude of that. So where a is equal to n minus 1 divided by 2, where n is given as a 13. So first we will find out a, 13 minus 1 divided by 2, that is 12 by 2 is equal to 6. So just put, so the phase of the linear phase FIR filter theta omega will be minus 6 omega. Okay. So option C is the correct answer for that question. Okay. Okay. So I hope you understand. So moving to the next question. Now next question is assertion and reason problem. So assertion is given as for a n-type FIR filter with coefficient Hn, its Z transform is given by h of z is equal to n, varies from 0 to n minus 1 h of n z to the power minus n, and reason is given as FIR filter uses delayed version of input signal to filter the input to the output. Okay, so option A is both A and R individually true, and R is the correct explanation of A, and option B is both A and R individually true. R is not the correct explanation of A. Option C is A is true, but R is false. Option D, A is false, but R is true. So which option will be the correct one? So here it is given for a n-type FIR filter with coefficient h of n, coefficient here h of n, its Z transform is given. Already we have seen. So that means A is the correct. Okay. So A assertion is correct. Now we will look into the reason. So FIR filter uses delayed version of the input signal to filter the input to the output. So already we have seen that FIR filter equation, that is y of n is equal to that n vary from 0 to n minus 1, right? Bk x n minus k. So here what we are using? The delayed version of input. Delayed version of input. And here, from here you can also see z to the power minus n represents the delay. Okay, that means the r is also true. So here they are saying that FIR filter uses delayed version of the input signal to filter the input to the output, to filter. That is also correct, and that is a correct explanation of A. So here the detailed region is given here, so you can uh, see it. So for n-type FIR filter with coefficient h of n, Z transform impulse response is this one. So this is a standard Z transform representation of an FIR filter, where each coefficient h of n is associated with the delayed version of z to the power minus n. And reason is given as FIR filter operates by applying a weighted sum of delayed version of the input signal, meaning they don't rely on the feedback like FIR filters. So FIR filters perform convolution with the finite duration impulse response with align with this region. So yes, because of Z transform representation of an FIR filter inherently arises from the fact that is implemented using delayed version of that input signal. So that makes R is the correct explanation of A. Okay, so option A is the correct answer for this question, that both A and R individually true, and R is the correct explanation of A. Okay, okay. Now I'm moving to the next question. Now next question is, if H of Z is the Z transform of the impulse response of an FIR filter, then which of the following relation is true? Which relation is holds true? So any one of you can answer to the chat box. Try to answer at least. Okay, so let's see. So as we know that I am writing from here, H of Z is equal to n is equal to 0 to n minus 1, H of n, right, z to the power minus n, and also it holds the symmetricity and anti-symmetricity property, right? That is H of n is equal to plus minus h and m minus 1 minus n, where n will vary n to n minus 1, right? Now what we need to do, so just transform it to the time reversed response. Transform of the time reverse. So time reversal property already you have seen in the many places. So if we replace n by m minus 1 minus n, then new Z transform in this equation, Z transform will be and also put at the place of Z to Z inverse. Okay. So or we can represent that VR because shifting, time reversing it. So it is represented by H of Z inverse. So new Z transform. N will vary 0 to m minus 1 till m minus 1, and H of N Z minus N minus m minus 1, right? M minus 1 minus n. So here we are just shifting n by m minus 1 minus n, right? So now, so by the property of symmetricity, antisymmetricity property, and also now what we need to do, just multiply z minus m minus 1 in both sides. So if you multiply z minus m minus 1 into z in this case, so I am writing it here, z to the power minus n. So you will get here, so summation we will vary to m minus 1 h of n z minus n minus m minus 1, and then follow the symmetricity property. So you will get it is equal to h of z plus minus h of z. So here you will get z m minus 1 and h z inverse is equal to plus minus h of z. So by symmetricity and symmetricity antisymmetricity property and multiplying both sides z minus 1, and you will get this relation is holds true. Okay, option C is the correct answer for this question. Okay, so I hope you understand it. So moving to the next question. Now next question is, a low pass FIR filter is designed using the following specification. So transition bandwidth is given 200 Hz, cutoff frequency is given 4 kHz, sampling frequency of the input signal is 10 kHz, and the filter is implemented using rectangular window. So here it is also filter is implemented using rectangular window. Then determine the order of the FIR filter. What will be the order of the FIR filter? So how we can solve this problem? Okay, so it is given the rectangular window is given, right? So what is the transition bandwidth for the rectangular window? Transition bandwidth for rectangular window, the distal of omega is equal to 4 pi by m, right? And if you further do that, so transition bandwidth is given, that is 200 Hertz equal to, and that we can write it like that, 2 into 2 pi by m. Now here m we need to determine m because they have determined the order of the filter. Okay, so that is m. Okay, and if you have gone through the video lectures, so sir has defined 2 pi is equal to the fs, that is sampling frequency or input frequency, that 2 pi is equal to fs. So if you further do that, so you will get 2 into fs divided by m. So here fm is given, that is 10 kilohertz, right? So further m is equal to 2 into 10 into 10 to the power 3 divided by 200, right? So now if you further solve it, you will get what is the order of that filter. 2 will be cancelled out, only 100. So order of the filter is 100. Order, that is m is equal to 100. Order of the FIR filter is equal to 100. Okay. Okay, so I hope you have understand. So moving to the next question. Now next question is design a low pass filter with with pass band edge frequency is 0.2 pi and stop band edge frequency is 0.3 pi, where pass band ripple equals to 0.01 dB and stop band ripple is also 0.01 dB. Sampling frequency is given 16 kHz. Now we have to design a low pass filter with these specifications are given. Okay. So what other things are required for designing a filter? That is transition bandwidth, order of the filter, low pass frequency, that is pass band and stop band both, and ripples. So these are the given. Sampling frequency is given. Now we have to find out the transition bandwidth and what will be the order of that filter. Okay, so these are the basic things what we are required to design a filter. So other things are given. What left? That is transition bandwidth and order of that filter, that is M. Now we need to determine these two parameters, okay, to design a filter. So here omega p is given as, that is pass band edge frequency is 0.2 pi, right? Omega s, that is stop band edge frequency is given as 0.3 pi, and the pass band ripples, that is del p, is given as 0.01 dB, and the stop band ripple is also is given as 0.01 dB, right? Now we need to determine the peak of that stop band, or it is also said as del 2 or del s. It is given in dB. We have to find out in another parameter. Okay, so del 2 is given as 0.01, that is equal to, already we know that, 20 log 10, that is del s, right? So minus 20 log 10 del s is equal to 0.01. If we put, sorry, if we put here, just a minute, del s is given, it is not equal to, so 0.01, so you will get 20 log 10. We can write it 10 to the power minus 2, right? So if you further solve it, you will get minus 40, sorry, plus 40, minus or minus will be the 40 dB you will get, that is del 2. Okay, now what is a main low? Transition with transition bandwidth, that is del omega, right? So already we know that what it is equal to omega s minus omega p. So already it is given. So 0.3 pi minus 0.2 pi, that is equal to 0.1 pi. So transition bandwidth we have got. Okay, now we need to find out the order of that filter. How we can find out? The transition bandwidth is given. So it has a relation between the transition bandwidth and the order of the filter, that already we know. Here no window function is given. So we have assumed that it is a Hamming window. So that is the transition bandwidth of a Hamming window is equal to 8 pi by m. You can take any other window function also, rectangular, Hamming, any other. Okay. So here I have taken the Hamming window. So you can try with the another window function also. Okay. So the transition bandwidth is equal to 1 pi is equal to 8 pi by m. Here it is not specified. So normally I have taken the Hamming window. If the window function is given, so you have to choose accordingly the Okay, that formula. So pi will be cancelled out. From here you will get 80, right? 8 divided by 0 0.1. So 0 0.1, if you just rearrange or solve it, you will get m is equal to 80. So order of the filter is 80 and transition bandwidth is 0 0.1. So and peak stop band ripple is also you have got 40 dB. Similarly, pass band ripple del 1 also will be the same, that is 0.40 dB if you find out. Okay. So these are the parameters which are used to design a low pass filter. So from here you can just, they have asked only parameters, so just when they have asked to design a low pass filter with this, so just you have to find out what are the other parameters you need to find. Okay, so just calculate those parameters. Okay, so transition bandwidth, order of the filter we have got, also the ripples, peak ripples and stop band and pass band also. Okay, so okay, moving to the next question, I hope you have understand. So here it is given design. Here also the another question is also related to designing of a filter, but here the given in form of kilohertz, not a radians. Okay, so design a low pass filter with pass band frequency fp is given as 2 kilohertz and stop band frequency fs is given as 2.5 kilohertz with attenuation of at least 40 dB. Okay, here that del S or del P they have directly given 40 dB. Let's the sampling frequency fs is 10 kilohertz. Using the technique you know, determine the design with the least number of coefficients. Okay, so that means m is equal to must be a least number of coefficients, lowest one. Okay, so now fp and fs is given. Now what we are required, omega s and omega p, right? So from here first we have to derive the omega s and omega p. So first we will see how we can got it. So pass band frequency omega p. So already if any signal or frequency is given in the form of f, so how we can determine in the form of omega? So there is a relation, right? 2 pi into f divided by fs. Similarly, we have to apply here also to 2 pi into ft divided by fs, right? So omega p you will get. So omega p is equal to 2 pi into ft is 2 kilohertz and fs is given as 10 kilohertz, right? So from here you will get further. So this will cancel out. So 5. Okay. So 2 pi by 5, right? Omega p you have got 2 pi by 5. Similarly, we need to find out omega s also. So 2 pi into fs. So here it is a capital one, right? And here it is a fs. So 2 into 2.5 kilohertz will be cancelled out. So I'm just writing it. Okay. So 4 jar. So here 2. Pi is also there. Okay. So that means pi by 2. So omega s and omega p we have you have got. So from here also the transition bandwidth we can find out. Transition bandwidth, that is del of omega is equal to omega s minus omega p. So omega s is pi by 2 minus omega p, that is 2 pi by 5. If you further solve it, you will get total pi by 10, right? Okay. Now I have to remove all those things. So Okay, so I'm writing it here. Okay, here. Now what they have determined the design with the least number of coefficients, that is m. Okay, so design with the least number of coefficients. So design with least number of coefficients, that already we know that the relation between transition bandwidth and the, so 8 pi by m must be equal to less than 2 the least number of coefficients. Okay, so this relation must be whole, less than or equal to transition bandwidth must be less than equal to 8 pi by m. So transition bandwidth is given pi by 10 must be equal to less than or equal to 8 pi by m. So pi and pi will be cancelled out. So m will here then must be less than equal to 80. Either it will be less than or equal to m is equal to 80. So that will carry the least number of coefficients. With these specification we can design. So least number of coefficient will be the 80 only. We can just take lower than 80 also. Okay. Okay, so I hope you have understand. So all the parameters we have got: omega p, omega s, transition bandwidth, and number of coefficients. What will be the least number of coefficients? Okay, okay. So I hope you are getting. So moving to the next question. Okay. So now next question is determine the value of h of 0, h of 1, h of 5 and h of 4, right, of a linear phase FIR filter of length m is equal to 6 with which has a symmetric unit sample response and a frequency response that satisfies the equation satisfies the condition as equation 2, that is equation 2. Okay, so this is a question related to your sampling method. Okay, frequency sampling method. So already you have seen that I will go to that formula. So here this formula will be used here. Okay, here alpha is not given, so alpha is equal to 0 we will use for this one. Okay, this one, either this one for symmetric and anti-symmetric function. So whatever the function is given. Okay, so either it is a symmetric or anti-symmetric based on that. Okay, so it is related to frequency sampling method. Okay, someone has something. So okay, so let's solve this problem. Okay, here given as okay, so here given m is equal to 16. Okay, sorry, m is equal to given as 6. Okay, and hr is given as this function. Okay, from there, so we will use this formula: gk is equal to minus 1 to the power k hr 2 pi by n into k, and h of n will be, because it has symmetric unit sample response, so symmetric one, that formula. Okay, so alpha value has been not described, so alpha will be count as a 0, so alpha is equal to 0 and symmetric one. So from there you can just see the formulas. So these are the formulas. So h of n is equal to 1 by n g of 0 plus 2, k will vary 0 to u, we will define u also, g of k. Now I am writing here, after that gk under summation it is okay, cos 2 pi k divided by n in multiplication with this under the cos only, okay, 1 plus 1 by 2, okay. And now how we will determine the u? So u will be n minus 1 divided by 2 for n is equal to odd, and n divided by 2 minus 1 when n is equal to even, okay. So first let's determine the u. So m is equal to 6, that is even, okay. So m is, sorry, here n, here it is given in the form of m, so we can write it, okay, m. So here m is given is equal to 6, so it is even, right. So this will be the m minus divided by 2 minus 1, you will get, so 6 divided by 2 minus 1, that is equal to 2, right. So u is equal to 2, you have got, okay. Now we need to determine the other parameters, that is g0, g, k and all those things, okay. So first we will determine from here directly. So g0 first we are determining, so g0, so g0 is equal to, so just put k is equal to 0 in this equation because k vary from 0 to u, so that means 0 to 2. So we have to find out g0, g1, g2, okay. So minus 1 to the power 0 in this equation, hr 2 pi by 6 into 0, so hr will be 0. So that means whatever in that k is equal to 0 place, so it is 0 place, it is 1 place, it is 2 place and all 3 place 4. So equation is minus 1 to the power 0, hr 0 value is 1 into 1, so you will get directly minus 1, g of 0 is equal to minus 1, oh sorry, not minus 1 to the power 1 only, so plus 1, okay. So plus 1. Now find out the g of 1, so minus 1 to the power 1 hr 2 pi by 6 into 1, right. So at one place it is value again 1, so minus 1 to the power 1, so minus 1, right. Now just I am removing it from here so that we can write. So I think you have noted down, or you can see in the video. So u value we have got, so no use of u, okay. We need this formula. So now g2, so just put, so minus 1 to the power 2 hr 2 pi by 6 into 2. So at the 2 place, so minus 1, so 1, and this place the value is 0 0.6. The value is 0 0.6. Okay. So just I am writing for our convenience. So g0 we have got, that is 1. G of 1 we have derived as minus 1, and g of 2 we have got is equal to 0 0.6. Now I am removing all this, okay, because now we have to put in this equation. Now we have to determine the h1, okay, no, first h of 0, h1, h5 and h4, okay. So first we will determine h of 0, that means putting in this equation 0, n is equal to 0, so n is 1 by 6, okay. G of 0 it is given as 1, 1 plus 2, So here k will vary from, okay, just 0 to 2 g of k into cos 2 pi k. N is 6, right? Here n is 0 plus 1 by 2. Okay, so that is closed. So now further, if you solve this, 1 by 6, 1 plus 2, it just open this summation. So g of 0, k is 0, so all the factor will be 0 only, right? K is 0, yes. So it will be the 0. G0 cos 0 plus G1 cos 2 pi by 6 into 1 by is 0. 1 is, no, it is, so into 1 by 2. Right, so 2, 3, so 1 pi by 6 only there, right? Plus G2 cos 2 pi into 2, 6 into 1 by 2. So 2 will be cancelled out. Pi by 3, here it will left. So 1 by 6, 1 plus 2. If you further just solve it, you will get cos 0 is 1, G0 is also 1. So 1 minus G1 is minus 1, right? So minus 1 into cos pi by 6. So minus cos pi by 6. G2 is 0 0.6, right? Cos pi by 3. Okay. So 1 by 6, 1 plus 2. Just you further solve it, you will get, if you put the values and just multiply this into this, so 2, here it is minus, so I'm just directly writing. You can further calculate it because I didn't also calculate it. So if you multiply 2 cos pi by 6 value, you can calculate and just write multiplied by 2, so you will get 1.732, and cos pi by 3 and just 0 0.6. So cos pi by 3, I think 1 by 2, so 2 will be cancelled out, so it is 0 0.6 only. Okay, now further, if you add and divide it by 6, you will get 0 0.3113. You will get it. Okay, just take calculator and calculate it. Okay, so h of 0, we have got 0 0.3113. So just I am writing here, h of 0 is equal to 0 0.3113. Okay, now what we next, h of 1 we need to calculate. Okay, so just I am removing it from here. So h of 0 is value we have calculated. Now we have to calculate h of 1. Okay, so now put n is equal to 1. So h of 1 equal to 1 by 6 g of 0 plus 2. After 2 I am writing here. Okay, summation k will vary 0 to 2 g of k cos 2 pi k divided by 6. N is 1, so 1 n 1 plus 1 by 2, you will get 3 by 2. So I'm just writing 3 by 2, but further you can solve it. So 3 2, so pi by 2k. So cos, if you further pi by 2k, this value we have got here, right? Just put n is equal to 1 in this, just solve it, so you will get pi by 2k. Okay, so just I am removing it here and directly writing cos pi by 2k. Okay, cos pi by 2k. Now further if we solve it, 1 by 6, g0 is 1, 1 plus 2, just open this summation, that is g0 again cos 0 plus g1 cos pi by 2 plus g2 cos pi, because k is equal to 2, so 2 will be cancelled out, cos pi. Okay, now 1 by 6, 1 plus 2, g0 value is 1, cos 0 is also 1, so 1, right? g0 and cos 0, that is 1, plus g1 is minus 1, cos pi by 2, what will be the value cos pi by 2? That is 0, cos pi by value is 0, so into 0 plus g2 is 0 0.6, cos pi value is, if you just sign, so you will get minus 1. Okay, so 1 by 6, 1 plus, so you will get 2, 1 minus 0 0.6. Okay, so if you further calculate it, so you will get 1 plus 0 0.8. Now further you will divide and add it. So 1.8 divided by 6, you will get 0 0.3. So h of 1 value you will get 0 0.3. Okay. So now you have got all those values. So h of 1 we have got 0 0.3. Just remember it. Okay. Okay. So I am writing h of 0. We have got 0 0.3113. H of 1 we have got 0 0.3. Right? So by symmetricity property, if you see by symmetry property, you can see that, say that h of 0 must be equal to h of 5, right? And h of 1 must be equal to h of 4, and h of 2 must be equal to h of 3, because m is equal to 6, right? So that values will be equal. So h of 0 and h of 5 will be equal. So they have asked h of 0, h of 1, h of 5 and h of 4. So we don't need to calculate h of 2 or h of 3. If you want, you can calculate it. Okay. So h of 0 is equal to h of 5. What we have got? 0 0.3113, and h of 1 is equal to h of, sorry, it is 5. So h of 4, that is equal to 0 0.3. So all these four values we have calculated. Okay. Okay. So I hope you have understand so this question. Now moving to the next question. This way you can calculate it. Okay. Otherwise it will be the very long question. Now moving to the next question. Which of the following window is used in the design of the low pass filter to have frequency response as shown in this figure? So which window function it is representing? Whether Hamming window, Henning window, Kaiser window or Blackman window? So which window function it is representing? Okay, so answer is already given. It is representing a Blackman window. So detailed analysis is given in the next slide. So answer is, so from here you can just see the main lobe, the width of the main lobe, and the what are the side lobes, what is the peak, this value. So all those things you have to calculate and just see whether which window function it is. So that's why it is important to see all window function, the frequency response of the all window function. Okay, so the detailed analysis is given. here already. So the magnitude response in that graph in the image shown is low pass filter with main lobe followed by a side lobe. Okay, it all window function have that one. So the transition from the pass band to stop band is smooth. Okay, that is smooth. Pass band to stop band. Here it is. It is smooth, not a blurry one. So the side lobes are significantly attenuated below the 80 dB if you just calculate it, the dB. So I have seen and calculated. So that suggests a window function that provide a smooth transition band while effective surpassing side lobes. So the Blackman window is highly tapered window that has a wide main lobe, slower transition but very low side lobes. So Blackman window has a very low side lobes. And in the magnitude response plot also, we observe the stop band attenuation reaches nearly minus 80 dB, and which matches the expected performance of the Blackman. And for Hamming window, it is minus 53 dB. Already you have seen that in that table. And you have Blackman window for attenuation level is approximately not equal to, but approximately minus 74 dB. So it is nearly equal to, mostly similar. Okay, so since the provided graph shows the smooth transition band and side lobe surpasses below minus 80 dB, so the correct window function is the Blackman window. Okay, so this is a Blackman window. Okay, you can see the other window functions, frequency response also. Okay, so now again the next question is design a discrete time low pass filter for a voice signal. The specification is given as pass band frequency is given 4 kilohertz with 0.8 dB ripple. Stop band frequency is given fs is equal to 4.5 kilohertz with 50 dB attenuation. Sampling frequency is fs is given to 22 kilohertz. Now determine a discrete time pass band and stop band frequencies. Discrete time pass band and stop band frequencies. The maximum and minimum values of mod of h of omega in the pass band and stop band, where h of omega is the filter's frequency response. Okay, so already we have solved how we can solve this omega s and omega p. We need to find out. So the relation between omega and s, already we know that, as we know that. Okay, omega is related, that is 2 pi f divided by fs. Omega p, first we need to find out 2 pi. Here it is given fp. Fp is 4 kilo. I can write it because fp divided by fs. Okay, so 2 pi into 4 kilohertz I'm not writing because it will be the cancelled out. Okay, so it is 22. So here you will get how much? Just you divide and multiply it. So you will get 0.36 pi. Okay, similarly calculate omega s also. So 2 pi into fs divided by sampling frequency. So 2 pi into 4.5 kilohertz. Okay, so 22 kilohertz. So omega s, if you divide and multiply it, you will get 0.41 pi. Okay, now the frequency response in pass band, we already know that the frequency response in the pass band is vary from 1 plus minus omega, 1 plus omega del, sorry, 1 plus del to 1 minus del. Okay, so first the pass band attenuation is given, or you can write it del p. So 20 log 10 1 plus del p is equal to given as 0.8 dB. Right, from here you can calculate del p. So if you further calculate it, you will get 1 plus del p is equal to 0.04, right? So passband and option A has been, we have got that passband frequency 0.365, stop band frequency 0.415. So I can remove them further. Just they have asked the maximum and minimum value of h of omega in the passband and stop band also. Okay. So if you further calculate u1 plus del p is equal to, you will get 10 to the power 0.004. Okay. Just I'm removing it here, otherwise we can't write. So option A we have calculated. Okay, I will write it. Okay, so here I'm just writing the solutions. So omega p we have got what value we have got, just a minute, that is 0.36 pi, and omega s we have got 0.41 pi. Okay, this is the answers. Now we are solving for answer V. What will be the maximum minimum value of h of omega in the pass band and stop band? Okay, so we have seen from till here 1 plus del p is equal to 10 to the power 0.04. Now if you solve this, you will get it 0.096. Okay, so that the frequency response within the pass band is in interval 1 plus minus del p. Already we know that is vary. So 1 plus del p, just h of omega. So 1 minus del p, already you have seen in the first or second slide. So if you further just calculate it, you will get 0.9035 h of omega will vary 1.096. Okay, so that is a pass band. Now further you have to calculate similarly in the stop band. In stop band, so 20 log 10 del s, that is 50 dB attenuation is given, that is equal to 50 dB. So log 10 del s is equal to 50 divided by 20, right? Now if you further calculate del s, that is 10 to the power 50 divided by 20, right? If you further just divide, calculate with the calculator, you will get 0.0031. Okay, so the maximum minimum value of h omega in the pass band and the stop band we have seen, that is in stop band and that is in the pass band. Okay, okay, so I hope you have understand. So moving to the next question, anyone have any doubt? Are you getting these questions? So okay, I hope all of you are getting. So moving to the next question. Now next question is, in the frequency sampling method for FIR filter design, we specify the desired frequency response SD of omega at a set of equally spaced frequency. Okay, they have given at a set of equally spaced frequency. So that is true, either true or false. So already you have seen type 1, type 2, and even and odd functions also. In that you have seen the type 1 where n is even, type 1 n is even and n is odd also, and then type 2 n is even. So they from there it is that question is. So in the frequency sampling method for a FIR filter, we specify the desired frequency response ST of omega at a set of equally spaced frequencies. So it is true or false. So already we know that we have seen the frequency, that is we are moving from one place to, so it is a equally spaced, right? Whether it is even or odd, it is divided by equally spaced. Okay. So in the frequency sampling method, we specify the frequency response HD of omega at a set of equally spaced frequency, namely that is omega k is equal to 2 pi by m k plus alpha, where k is the vary and alpha can be a 0 or 1 by 2. So it is set of equally spaced frequencies. So this is true. Okay. So this content is true. Okay. So in the frequency sampling method, we specify desired frequency response at a set of equally spaced frequencies. Okay. Okay. So I hope you are getting. So moving to the next question. Oh, a detailed explanation is given also. So the frequency sampling method or FIR filter design work specifically a desired frequency response ST of omega at a set of equally spaced discrete frequencies. Okay, the desired frequency response ST of omega is sampled at an equally spaced point. Already we have seen that 2 pi k divided by n, where k is very 0 to n minus 1. Okay, and other details are also given, and also there is a k is also 2 pi k and that is alpha, k plus alpha is also there. That alpha part either 0, it is 1. You can see it. So invert discrete IDFT to obtain Hn, the corresponding impulse response coefficient Hn are obtained by taking the inverse DFT of that samples. And we must to ensure that it is FIR filter must be linear phase. So we will decide based on that. Okay. Okay. So moving to the next question. Okay. So here it is given if the order of the filter as described in the question number 12 is double and the design using Hamming window, then what will be the transition bandwidth? So if you are designing, so transition bandwidth for Hamming window, already we know that transition bandwidth for Hamming window, that is del of omega is equal to 8 pi by already we know that. Now just let's see what is the order in the filter as described in the question number 12. What will be the order we have derived from there? Okay, so here the order of the filter we have derived, that is 100. Okay, so order of the filter in question 12 is 100. Okay, so order of the filter, order of the filter in question 12 is what we have derived is m, that is m is equal to 100, right? It is given. So now they have, if the order of the filter is described in the question 12 is double. Okay, if this order is double, so we can see that, say that 200. Okay, that means 100 is double, that is 200 will be there. So what will be the transition bandwidth for Hamming window? So the transition, it is 8 pi by 200, already we know that. Okay, 8 pi by 200 because order we have got. So but 8 pi, how we can write it? So 4 into 2 pi divided by 200, and that 2 pi we already know that represent a sampling frequency. So sampling frequency in that question is given as 10 kilohertz. 10 kilohertz you can see from that here. 4 into 10 kilohertz divided by 200. Okay, so from here you will get again the bandwidth, you will get 200 hertz. So del omega you will get del 200 hertz. So the transition bandwidth for Humming window is 200 hertz. Okay. Okay, so I hope you have understand this question. Now moving to the next question. Now next question is, the roots of the polynomial h of z are identical to the roots of the polynomial h of z inverse. That means h of z must be equal to h of z inverse. So whether this content is true or false. So already we have described this equation, right? Already we know that, as we know that z m minus 1 h of z inverse is equal to plus minus z inverse. So this result implies the roots of the polynomial h of z are identical to the roots of the polynomial h of z. Okay, so that means this content is holds true. Okay, so from here we can say that the polynomial equation must be identical. The roots must be identical in both. Okay. Okay. So now the questions have been complete. Now if you have any doubt you can ask, otherwise we can close the session. Okay. Anyone of you any, have any doubt? So now you can ask, otherwise we can close the session. Yeah, Anis, any doubt? If you don't have any doubt, you can leave the session and you can, otherwise we can close the session. Okay. So thank you everyone. Thank you for joining this session. If you don't have any doubt, then we can close the session. Please ask your queries if you have any. Anyone have any query? Any doubt? Okay, so I am waiting for 2 more minutes. If you don't have any doubt, then I will just close the session. Okay. Okay, so I hope any one of you don't have any doubt. So just I'm closing this session. So thank you everyone. Thank you for joining this session. we will I will see you in the next session. Okay. So thank you for joining this session.